Before we get into the nitty-gritty of strain sensing, let's review very briefly what we mean by stress and strain. And in this case, I'm assuming I have a cylindrical bar of some material. It has a length L and a diameter D, and I'm applying a force at the end of it defined by F. And so when I apply that force, I stretch the bar by some amount delta L, and as a result of stretching the bar also contracts in diameter some d minus delta d. So that's the new diameter, so it contracts a delta d. Based on this example, I can define a couple important parameters for my system. Normal stress would be the first one. That's defined by sigma, and that's going to be the force over the area on which that force is applied. So in this case, this area right here. I also have my axial strain. And that axial strain is written as an epsilon, A in this case, is going to be that change in length divided by the length, right? So that delta L divided by the original length of the bar right here, L. My transverse strain is defined by the change in diameter. Epsilon T is going to be that change in diameter over the initial diameter of the bar. And these two terms together are going to give me Poisson's ratio, where nu is defined as the negative of the transverse strain over the axial strain. And that's always going to be greater than 0 and less than 0.5. And some key points to remember for strain: it can be tensile or compressive. Where tensile strain is typically defined as positive and compressive strain is defined as negative. Strain is also dimensionless. It's also important to point out that often the strains that you're measuring are going to be really small, and so kind of in the same vein as this dimensionless measurement, you have very small strains that are often measured in microstrain. So in that case, you might have a strain with units microstrain, which are still meter per meter units, still dimensionless number, but in this case, it's the original strain times 10 to the 6. So if I had a strain that was 10 to the minus 6 meter per meter, that would be 1 microstrain. To measure strain, we're going to use strain gauges, and often you see it written as GAUGES or GAGES. But those resistive strain gauges are fairly similar, in some sense, to the beam that we just analyzed. It's a chunk of something. And in this case, I'm going to give that chunk of something a length L, right? Oftentimes they're metal. It'll have an area A. If I were to set that up in a circuit, say as a chunk of metal of some sort, apply a V in on one side of it and connect that to the other side there, I'd be measuring a resistance here. And that resistance of this block of metal is going to be dependent on the geometry, so its length divided by its area. So I'll have a lower resistance if I have a bigger area of my chunk of metal, or a higher resistance if I have a longer chunk of metal. And then I have one other parameter here that I'm going to call rho. And rho is a material property associated with whatever material I'm making this chunk of metal out of, or chunk of whatever. And I can check my units of this. So rho is what we define. This is the resistivity of my material. That is given in units ohm centimeter. So I have units of ohm centimeter times, let's give myself a length in centimeters, and an area then in centimeters squared. So out of this, I will get a resistance in ohms. So it's always a good way to check that you have your L and your A, for example, in the right place when calculating your resistance, is to look at your units once again. So in this resistance, I have some geometric properties, and that's my length and my area. And if I pull on it, if I strain that material that's creating that resistance, that's going to have a similar effect to what we just looked at. Right? I'll lengthen that material and I'll contract it. And so we'll see how that leads to changes in resistance. And I also have an intrinsic material property, and that's my resistivity rho. And this really comes into play when I have a material like a semiconductor or some conductive polymers as well, because this resistivity is actually going to change based on strain too. But for metals, it's really only the geometric property, and that's what most strain gauges are made out of. So what I'm interested in is if I have, let's just look at a chunk of metal to simplify our lives to start, and I have a resistance associated with that chunk of metal based on its geometric properties and its resistivity, that's in this case for metal not changing with any strains applied. And this is the nominal resistance of this. Now I've strained that material some delta L. So I have a new resistance here that's based on that same resistivity, but now my length is an L plus a delta L, and my area is an area minus a delta A here. And I'm interested in figuring out what my delta R is. So effectively the difference between that new resistance and the nominal resistance. So to do that, I'd like to take the derivative of this function right here, but that's a little complex to do. So I'm going to take the logarithmic derivative of this function here. So I'm going to take effectively natural log of R is rho L over A. And remember, this is all trying to figure out what this change in resistance is based on some kind of strain input. So in this case, I'm going to get the natural log of R is equal to the natural log of my resistivity plus the natural log of my length minus the natural log of area, right? Because that's in the denominator here. And I know from calculus that if I take the derivative of the natural log of x, then I will get 1 over x dx, or dx over x. So if I do this up here, I'm going to get dr over r is equal to d rho over rho plus dl over l minus dA over A. So I've rewritten that equation here, and my dr here is going to give me my delta r, right? That's ultimately what I'm interested in. This d rho over rho term is going to be based on any piezoresistivity I might have in my sensor. Right? The dl over L term, that's effectively my strain that I'm looking at, right? So I'm just going to write this as my strain. In this case, I'm going to assume an axial strain. And then I have this dA over A term. And for that, it helps us to go back to our kind of cylinder of material example, right? So my A right here, my area, is equal to 1/4 pi d squared, where d was my diameter. And so if I look at that dA over A term, then that is going to be equal in the denominator 1/4 pi d squared, and the derivative, I'm looking at 1/2 pi d dd here. So this is going to give me 2 times the change in d over d, which is that diameter. And remember, this is effectively my transverse strain. So this term right here is equal to minus nu times my axial strain. So that dA over A term is going to end up giving me minus 2 nu times the axial strain. So if I rewrite this dr over r equation here, dr over r is going to be equal to, I'm going to put these two terms first here, so 1 plus 2 nu times that axial strain, and then I still have that resistivity term right here. So it turns out I can actually simplify this based on a piezoresistive coefficient that I'm going to call pi A times the elastic modulus of the material and the strain that I'm applying. Right, so I won't go through the derivation of this, but this pi A term, this piezoresistive coefficient, is going to depend on the material that I'm using. So now I can really simplify this term to 1 plus 2 nu plus pi A times E, all of that times strain. And so the interesting thing here is that I have two kind of bits to this. So I have a geometry factor, And this is what we'll see most with metal strain gauges, for example. And then I have a piezoresistive factor here, and this is what I might see with semiconductor strain gauges, for example. Right? This will be dominant in semiconductor strain gauges and negligible for a metal strain gauge. Let me just rewrite that for simplicity. So I'm going to have dr over r. That's effectively the output of my strain sensor. So I'm interested in that change in resistance over the nominal resistance. I have my input, which in this case is an axial strain applied to my strain sensor. And then this term right here, I'm going to give a special name, and I'm going to call that the gauge factor, or you'll often see that written as GF. So we also define that gauge factor as my change in resistance over the nominal resistance, divided by the change in length over the length, my strain. So that's delta R over delta L over L. So this is unique to strain gauges, right? Because we're using strain as part of the definition for our gauge factor. And using that gauge factor, I could then compute, for example, what my axial strain was based on changes in resistance that I'm measuring. So my delta R over R is going times 1 over the gauge factor is going to give me back my axial strain that I'm ultimately interested in. Right? So I'm in this case trying to measure a strain. I might have a Wheatstone bridge that I pull a voltage out of. Right? That voltage informs what my change in resistance is, and then based on knowing about my strain gauges and my gauge factor of my strain gauges, I can compute what the axial strain that I'm interested in is. So let's work through an example really quickly to see what kind of changes in resistance we might expect for strains that we might see. So a metal foil strain gauge might look something like this. I have this path of typically something like copper that's winding along here to give myself a reasonable resistance. So in this case, let's assume our nominal resistance is something like 120 ohms. And because it's a metal strain gauge, I'm going to have a gauge factor of 2. Let's say a polysilicon strain gauge or some other semiconductor strain gauge might have a gauge factor of a couple hundred as a counterpoint. And in this case, I'm applying a 1 microstrain strain to this strain gauge. So I know that my strain is going to be 1 over the gauge factor times delta R over R. So if I'm interested in figuring out what delta R is, I can just manipulate this equation, as delta R is the gauge factor times the nominal resistance times the strain that I'm applying. I can plug my numbers in here. 2 is my gauge factor times 120 ohms times 1 microstrain, so just 10 to the minus 6. So my change in resistance is going to be 240 times 10 to the minus 6 ohms, or 0.24 milliohms, which is pretty small. So if I think of what my new resistance is, where it was the nominal resistance plus that delta R, now I'm looking at 120.00024 ohms. So you can see why we might want decent interface electronics that give us decent sensitivity, as well as ultimately amplification off of our Wheatstone bridge as well.